Alright guys, let's go ahead and take a look at the Unit 8 Extra Credit Review. Not 9.1 and 9.2. Okay. So, at the beginning of Unit 8, we kind of talked about interpreting like rate time graphs, velocity time graphs. So here we have a velocity time graph, okay? Velocity in miles per hour, time, hours, alright? Okay, what is the bicycle's velocity at 12:30? And this is hours afternoon. So if this is noon, it's time 0, okay? 12:30 would be right here. Now you don't have to estimate because, you can see if I go up 30 over 1, halfway would be up 15 over half, right? Okay, so that would be 15 miles per hour. At what time was the bicycle at rest? Now you got to know those words here, okay? And at rest is when the velocity is 0. So if I take a look at this, we are at rest from here to here, okay? So from 1, is this like PM? Yeah, PM to 3 PM. What is the bicycle's acceleration at 12:30? Now, acceleration is the derivative of velocity, which means that this is going to be the slope of the velocity. And so if I come over here and I need to find, right, the slope of that line, we already looked at it, but it's rise over run. So up 30 over 1. So the acceleration is 30 over 1. Now, we take that miles per hour. If we do a derivative of that, it's miles per hour, or you can put miles per hour squared, okay? Then we're doing another acceleration, this time at 3:30. We'll label our units on there too. Okay, 3:30 is right here. So it goes down 10 over 1. Because remember, make sure you pay attention to the labels, okay? Down 10 over 1. So it's going to be a negative 10 miles per hour squared. All right, find the integral from 0 to 4. Okay, here's where we're going to use a little bit of geometry. All right, let me erase what I've got here. Okay, so I'm going to do a triangle. All right, a rectangle. And, you can do a triangle and a rectangle here, or you can do like a trapezoid. Whatever you want. Okay, again, remember your label. So this goes over 1, up 30. And triangles are 1/2 base times height. So that's going to be 15. This goes over 3 and up 30. And it's a rectangle, so that's going to be 90. Okay, this one goes, oh shoot, that only goes over 2. Just kidding. Over 2 times 30, that's going to be 60. And then over 1 times 20 is going to be 20 for that guy. And then 1/2 base and the height is 10. So that little guy right there is going to be 5. Okay? But when I add all those up together, that's 60, 70, 80, 90, 100. That gives me 100. Why do complete sense to explain the meaning of problem 5? Okay? The big idea of this section is that when we go, backwards from velocity, and that's basically what we're doing, right? Because this is the integral of velocity. You get an amount, or you get like a distance or something like that, right? And so what we're going to say is, what is this, the bicyclist went a distance of 100 miles. Because when I go backwards from miles per hour, it's miles. Okay? Okay, you guys, this is a very, very classic spam question. The bicycle's initial position is given by S of 0 is -4. Find S of 4. Okay, so we go like this. S of 0 plus the integral from 0 to 4 of the derivative equals S of 4. Now, what is the derivative of position? It's just velocity. So you can actually just think about this as velocity. And we just found that. So if his initial distance was -4 and we just went 0 to 4, which is 100, at 4 p.m. he's 96 miles from his starting point. That would be like his position. Okay. Okay, guys, it's not a video if I don't make a mistake. So let's go back and correct my mistakes. This was my mistake. Hopefully you guys caught that on number 2. You know, what I gave between 1 and 3 p.m., that's when the acceleration is 0. That means that the guy's like going constant 30 miles an hour. He's not speeding up. He's not slowing down. I screwed that one up. Velocity is 0. This is the velocity graph. So raise your hand if you knew I made a mistake. Okay. The velocity, the only time that the velocity is 0 is actually right there. So I need to change that. The only time the velocity is 0 is at noon. Okay. All right. Let's see if we can go through this next one with no mistakes. Okay. All right. This is mostly area stuff. Remember that area, you do it one of 2 ways. Okay. Top curve minus bottom curve from left endpoint to right endpoint. That's as a dx, okay? Or we can do right curve minus left curve from bottom to top. That's if we're working as a dy. All right? Okay, so first question here. The graphs of f of x are x squared minus 2x. That's going to be this one, right? Okay, because it's the parabola. And then g of x is negative 2x plus 4. That's the line. And it actually gives me the intersection points, which is lovely. So, set up. I am only setting up, you guys. I'm not integrating this. The one on the top is the line, so it's negative 2x plus 4. The one on the bottom is the parabola, x squared minus 2x. And we go from x coordinate to x coordinate when we do dx, all right? Because we're going like top to bottom, left to right. So this one's going to be negative 2 to 2, okay? Okay, now our next one, you can kind of tell that this one is x equals, that's this curve right here. It's a sideways parabola, so I'm definitely going to do a dy on this one. And then the other one is just the graph negative 1, which is right here. Okay, so when I set this up, it's going to be right minus left. It's going to be a dy, and then I use the y coordinates, and I go from bottom to top. So I'm going to go on this one 0 to 4. Okay, next, if we're given a graph, or, you know, a couple of graphs, and we're asked to find intersection points, like sometimes you can see them, but if not, you have to solve an equation here. And so what I'm going to do is set these equal to each other. You want to get everything on one side when you do this, okay? I'm going to add to this to the left because I like having all my variables on the left. I think it's a little cleaner. I like my first variable to be positive. Okay, so I get x to the third, and that's 1 minus 2, so minus x squared minus 2x equals 0, and I need to factor that. Now the first thing I'm going to do to factor is take out an x. Okay, and then I factor out the inside. So I get x minus 2, x plus 1 is 0. And so I end up getting x is 0 to negative 1. Now, this did ask me, if you noticed up here, to find the points of intersection, which does mean I have to find the x and the y coordinates. Okay, so clearly the x coordinate is negative 1. Clearly the x coordinate is 0, and then this is 2. And, you know, it's where they're equal to each other, so you really could plug it into either one of these. To find the y coordinate, I'm going to plug into that one. So when I plug in negative 1 squared minus 2 times negative 1, that gives me 1 plus 2, so that one's 3. That looks accurate with the graph. When I plug in 0, I get 0. That also looks accurate. And then when I plug in 2, I get 2 squared minus 2 times 2, 4 minus 4. Okay, and I get 0. And those are my 3 intersection points. All right? Box my answers here. Okay. Show an integral expression for the shaded area shown. Show an integral expression for the area shown by the graphs in problem 3. All right, excellent. So you guys, there are 2 ways to do this. The first is I split it up into like a region 1 and a region 2 kind of thing, okay? And I go, remember it's a dx because I'm going top minus bottom, so I go -1 up to 0. And in that part, let's see here, we have a parabola and a cubic. I gotta like draw this. I think that's the cubic. So I know this is the parabola right here. Okay, so the one I marked in blue is the parabola. That one's a little tricky to see. So, all right, I'm going to start region 1 with the parabola being on top. And by the way, if you want, you can just write f of x because it's shown to you as f of x minus g of x. And then the next one, from 0 to 2, they flip around. So it's g of x minus f of x. Okay, where the cubic is on the top and the parabola is on the bottom. Okay, perfect. The other way you can do this, and you kind of only do this when you're working with a calculator, I can go all the way, -1 to 2, and not separate out the integrals. But what you do is you just put an absolute value around it. And it doesn't matter which order you put f of x and g of x in. As long as you have an absolute value, it will give you the same answer there. Okay, cool. Let's go on to the next part. Now, in 8.3 is when we started learning volumes, and we were specifically using cross sections. 8.3 was like cross sections, okay? All right, so these, oh my goodness, 7 questions are all based on this one graph, so we better draw this carefully. Okay, draw it over here. Now, you guys know that this is a parabola. What I would do to tell what this parabola looks like, let's say we factor out like an x. And I set it equal to 0. I get x is 0 and x is 3. Okay, so it's an upside down parabola going through 0 and 3. So that's pretty easy to draw that. Okay. And then the other one is just the line 0. All right. So sketch a graph of the region. Okay, did that. Set up an integral for the area of this region. Okay. So the area is going to be top minus bottom You don't have to put the minus 0 there, obviously, and then from 0 to 3. Okay, set up an integral for the volume of a solid with a base of this region and square cross sections. All right, let me do that better. Okay, square cross sections. Perpendicular to the x-axis, so it's going to be a dx. So, okay, so picture this, and then we're making a square out of it, right? Now, the distance of that is just like the y value of it going up, which is this base right here is negative x squared plus 3x, okay? Which means since it's a square, that this side is also negative x squared plus 3x, which means the integral is negative x squared plus 3x times itself from 0 to 3, okay? Okay, now we're going to do same thing. The solid base of region, semicircle cross section. Semicircles are like a little bit more difficult because, you know, we've talked about this. You have to remember 1/2 pi r squared. But then you also have to remember that we're using radius, not diameter. So if I go in here, okay, let me take this away. Let's make a semicircle. Okay, that's the diameter. which means that the radius is that over 2. Okay, it's just half of that distance. And so when I set this up, 0 to 3, it's going to be 1/2 pi r squared. And the r is negative x squared plus 3x over 2. Okay, so that's how we would set up that one. All right, now we've got a volume question. Okay, so we're switching from cross sections to volume. All right. I don't want to keep like scrolling, so I'm going to draw it again down here. Okay, because we know what it looks like. It's just this upside down parabola. It's like negative x squared plus 3x. And this is the shaded region because it just goes right up against the axis. Okay. Set up an integral for the volume of that solid formed by revolving it around the x-axis. When I revolve this around the x-axis, you guys, this is a disk. Okay, because there's the boundary line of the region goes right up to the thing I'm revolving it around. And so, all right, it's going to be, let's see here. Remember with revolution, so the word that I'm looking for here is when it says by revolving. Okay, anything about revolving is pi radius squared. You can put the pi on the inside or the outside, doesn't matter. Pi r squared. Okay, this one we just have a single r, and it's negative x squared plus 3x. So that's what I'm going to put in here. Still going 0 to 3. Okay, it's just pi r squared. Okay, now we're revolving it around the line y equals 4. This makes it a bit more difficult. Okay, let's say that's the line y equals 4. All right, and I'm revolving it around, like up above that. Okay, the outer radius goes there to there. Right? It hits the edge of that boundary line. That's the outer radius. The outer radius is just 4. Now, the inner radius goes here to here. Okay, but the bottom part is x squared, negative x squared plus 3x. And so it's 4 minus that. I have to put another set of parentheses. Like that. Okay. So, let's see here. Pi, still going 0 to 3. Big R squared minus little r squared dx. I kind of ran out of room here. Okay. So with volume rotations, we're just always thinking pi r squared and getting the radius and stuff. With volume cross sections, we're integrating the area of that shape. All right. Let's see, that was number 6. Okay, good. And then last, you do need to know average value of the function. Average value goes like this. 1 over b minus a, the integral from a to b of the function. Okay, so the average value of this function would be 1 over 3 minus 0, because that's where I'm going from, 0 to 3. 1 over 3 minus 0. Oh, actually, I'm sorry. It says on the interval 0 to 4. So I'm wrong. But I got that one. Okay, 1 over 4 minus 0, the integral from 0 to 4 of my function. And then that's my answer. Okay? Okay, perfect. And here's a little extra problem. And then this looks like this was the 2006 question. So we'll go over that. Another extra problem. And then the 2005 question. Oof, so many questions. Okay. That's all right. We got this. Okay, you guys. Now, e to the negative x is kind of a tricky graph. But if you know e to the x, which goes to the point 0, 1, and it goes up like this, putting a negative in, what that does to a graph, and when it's in where the x is it flips it left to right. If the negative's in front, it flips it up to down. So this is actually going to flip that way. Okay. Show an integral set up for each of the following. Okay. So it's given the region in the first quadrant between the graphs of that and y equals 0. So first quadrant would be all of this right here. Area of the region. Okay, my friends, this is a BC topic. I will show it to you very, very quickly, but this is actually a BC only topic, I think. Maybe I'm wrong. I don't know. I don't know if we talked about improper integrals, but basically the integral of the region is 0 to infinity of, e to the negative x. Okay? And it's a little tricky. Again, I'm pretty sure this is a BC only topic, but what we do is we let b equal infinity, and we have to do the problem, or actually, we go like this. We let the top be b, and we say it's the limit as b approaches infinity of that, as b is going to infinity. We don't have to write that. Okay? And you basically do the whole problem with b, and you do the limit at the end. So the integral of e to the negative x is negative e to the negative x. Okay? And again, I write limit as b goes to infinity. And when I go to evaluate this, well, e to the negative x, it's a little easier to think of it as 1 over e to the x. So it's negative 1 over e to the b and negative 1 over e to the 0. Limit as b goes to infinity. Well, as b goes to infinity, what's going to happen here is that that's going to go to an infinitely large number, and 1 over an infinitely large number goes to 0. Then over here, e to the 0 is 1, so this ends up being plus 1 over 1. Okay, so even out to infinity, that's 1. The volume, same idea. We would go 0 to infinity. Let's see, the volume rotating around the x-axis would be pi r squared. Okay, and again, you can figure it out, but we'll just set it up. Okay. All right, we're going to get through this problem, and then I think my next video covers the next few problems. So here we go. Okay, let R be the shaded region bounded by the graph of y equals ln of x, that's this graph, and y equals x minus 2, that's the line. Find the area. Okay, so the area is going to be, oh, this is a calculator question, that's nice. Top minus bottom, and then intersection point to intersection point, which we were not given. So what we have to do is, let me pull my calculator up, go put in our y equals ln of x and x minus 2. Let's go look at the graph. Let's calculate these intersection points. So the first intersection point, so I'm going to come over to about right here and just push enter, enter, enter. And then that's my intersection point. It's like 0.158. So on here I'm going to actually write let a equal that. But what I'm going to do is I'm going to go out here and I'm going to go x store a. So it's in there, okay? Now I go back to the graph, I calculate the intersect, and I move closer over to here, and I hit enter 3 times. Okay? So it's like 3.146. So on my paper, I'm going to write let b equal 3.146. But on here, I'm going to go x, because now it rewrote over the last one, store b. Okay? Now, okay, the ln is in y1, x minus 2 is in y2, and the y1 is on top. So now I'm going to go like this. The integral from a to b of alpha trace, y1 was on top, minus alpha trace, y2 was on the bottom. Okay? And then that integral ends up being 1.949. All right? Okay, so we can kind of do all that. On the calculator, that's where I wrote let A and B equal. Find the volume of the solid generated when R is rotated around the horizontal line, Y is -3. Okay, let me draw that. So -3 is like down below both of those. Okay, so let's see here. The outer radius goes to there, so it's 3 plus ln of x. So outer radius is 3 plus ln of x. And then the inner radius, I'm going to do it on the positive side just so I don't get like confused, goes to there. So it's 3 plus x minus 2. Okay, so it's just like 3 plus on both of those. Let's see here. And so when I put it in, it's pi. It's still a to b, and we already defined that, so we can let it like that. And then it's going to be, if you write big R, little r, you could just write big R, little r. I'm going to write 3 plus ln of x squared minus 3 plus x minus 2 squared. Okay, and let's go ahead and go calculate that. So on my calculator, I'm going to go pi, and then integral from a to b. And the first one is 3 plus ln of x, which I have under y1, squared minus 3 plus x minus 2, which I have under y2, squared. So big R squared minus little r squared. Boom, 34.198. Okay, and then last one that we're going to do in this video, write but do not evaluate an integral expression that can be used to find the volume of the solid when R is rotated about the y-axis. Okay, this one's like a bit tricky, guys, because you have to change both of your equations, right? So, like, I have to change that equation to solve for x. Well, if y is ln of x, remember how you go like e to both sides? X is e to the y. And then right here, if y is x minus 2, x is y plus 2. Okay? Now it's still a big R minus a little r. And I actually can't use a and b anymore because I have to switch the x and y coordinates. All right? So I got to go find new coordinates. That's a little annoying. All right. And then I have to go... The line is now the furthest one away. So it's y plus 2 squared minus, and then the curve, e to the y squared, dy. Let's see, are we good? Yep, and it says write but do not evaluate. So the last thing I need is my points. Now, this is a little bit annoying because I had my points, but I'm not evaluating, so that's okay. So go back to the graph, calculate, intersect. This time I'm looking for the y-coordinate, okay? Make sure it's on the thing there. Okay, the y-coordinate is negative 1.841. And then calculate, intersect, go up here. And I've got the y-coordinate is 1.146. Cool. And then this one just said write but do not evaluate, so we're done. All right. Now skip over to part 2 to see the rest of these.